Alrighty, good evening and greetings, minions. My name is Nathan. I am a PhD student in chemistry, and I am a really big nerd who enjoys this enough to do it in my free time and keep talking about chemistry. Um, so, I had a brief moment where I was trying to think if I had anything to talk about today other than just doing some chemistry. I don't think that I do, which is a very tentative statement, because just give it a little bit of time. I can pretty much promise you I'm going to get distracted at some point and go down some rabbit trail and start just talking about whatever's on my brain. But for now, that is essentially nothing. So let's just hop right into it a bit. So, last day we were talking about some stuff that was way over here on the whiteboard. We were talking about electron configurations and how we fill them up, how we place them into different orbitals, and how that relates to the different set of quantum numbers for each electron. The quantum numbers being essentially just the address of each individual electron in an electron configuration, and how those follow the alpha rule, where we always fill the lowest energy orbitals that are available, and the Pauli exclusion principle, which states that no two electrons can occupy the same orbital and state, being spin up or spin down, or to put it another way, no two electrons can have the exact same set of quantum numbers, because that is just simply not allowed by quantum physics. Has to do with them both being electrons are, well, they're leptons, which is the more specific category of particle that they are. They're part of a different family of particles. I think it might be fermions, but I'm not. I wouldn't put money on that. But essentially, the rules of the quantum physics there is that you cannot have two of these particles in the same quantum state in the same location. And so just basically just using those two rules, we can we have a very specific order that we fill up orbitals in, just according to their energy, and also of note is like when you have multiple degenerate energy levels, which is like just p orbitals out in the wild. The px, the py, the pz, they all have exactly the same energy. The thing that differentiates them is simply their orientation in space. Well, actually, I guess a more correct way would be the orientation of their angular momentum. Don't worry about it too much; it's fine. But essentially, the p orbitals, absent of other influences, will all have exactly the same energy, and so, like the alpha rule tells us that we fill the lowest energy orbitals first. So to take that a step further, it means that these p orbitals, when they've got the same energy, there's no preference for what you fill first. It could be a px, a py, a pz. It makes no difference, because these are so-called degenerate orbitals that have the exact same energy. However, when you start to fill them up, first of all, we fill each of the p orbitals with one electron first before we start to pair electrons, and that is because of this kind of a principle, where it is it causes less electron-electron repulsion to singly fill two orbitals instead of filling one orbital twice. So in this one, the px orbital has two electrons in it, the py has none, Whereas in this diagram, they've got one in each. These correspond to these electron configurations. And this one is the lower in energy. I know it says higher energy pointing to this, but that's dealing with a different issue, which I'll get to in a moment. But comparing these two situations, where we have a double-filled orbital or two singly filled, this is going to be the lower energy configuration, because 95% of all of chemistry is just based around trying to minimize electron-electron repulsion as much as we can, and this is how we accomplish that. Now, the reason that this says higher energy is with reference to this configuration versus this one, and the difference here is that this has a spin up electron in the px orbital and a spin down electron in the py. And so having those anti-aligned spins is a higher energy state than having them both aligned. And you can think of this in terms of just having bar magnets next to each other. It's not a perfect analogy. Don't take this as the actual situation that is happening. But when you have these two situations, if you have the actually this might be quite a terrible analogy, because it is in fact dealing with different issues. For a moment I thought it was a good example. I don't think it is. So essentially this deals with the orientation of the magnetic fields of the electrons, and when they are aligned with each other, it causes less repulsion than when they are anti-aligned to one another. And so when we're filling the p orbitals, or any degenerate orbitals, because this applies to d orbitals as well, having them aligned with each other is favorable compared to having them anti-aligned. So that's what we talked about last day. So now let's talk about something completely different. I had briefly started going over this alkene addition reaction. And so when we're looking at this, we've got this molecule as a reactant, and we have iodine, I2, as another reactant. The sodium bicarbonate is just kind of there. We'll use it when we need it, but it's not itself particularly reactive, so we're going to kind of ignore it. Hello, Cheesy Stuffed Cakes. It is lovely to see you. I hope you're having a good week so far. Yeah, so in this reaction, we essentially have to choose what are the most reactive sites, and usually when we're talking about that, we're going to be looking at things like nucleophiles or electrophiles. In different circumstances, we might be looking at what's the strongest acid and the strongest base. And so there's different criteria that we can use, but because I am ever so smart, I can tell you this is looking at a nucleophile electrophile relationship. I'm glad you've been having a good week, and mine has been pretty good. Had a pretty restful weekend, and then yesterday it was a holiday up here in the frozen north, and one of my good friends from out of town came to visit. We had a great time, and today I've just been chilling. So I tried to read the crystal structure paper, was only able to access the abstract without a paywall. Really? This is upsetting to me, because I'm pretty sure that was published open access, but I wonder if I'm wrong. Okay, I tell you what, I'm going to take a quick look for it. Happy insert holiday, I love that. Yeah, it was what was it? It was Victoria Day. Yeah, which really means basically nothing to me, but yeah, it was nice to have a holiday, so thank you. On the ACS one, if it helps, could we have to log in some sort of thing? You shouldn't have to. Just let me quickly look up some stuff, like look up the link about it, because I certainly hope I'm not wrong, but it would not be the first time. Ba-dum-bum-bum. Okay, so let's see. Web link browser. Yeah, so that's the thing. I don't want to cite it. I just want to see the thing. Boo. Oh, that's right, because I went to the citation link. This will probably be more helpful. Oh, okay, so this. I am irritated. I need to go. I think I need to go back through my correspondence with my prof, because I'm sure that we publish this open access, but I wonder if there's a limited time that they leave it open access. Yeah. No, that is all right. I'm glad to know about it. So yeah, I'll double check on that. Oh my gosh, I didn't realize 420 people view. That's lovely. Anyways, but yeah, so that's irritating. But what I'll tell you is, so I have no idea if I am I would have to look up some terms of service or codes of use. I don't know if I'm allowed to show this stuff on Twitch per se, but there's most certainly a way that you can get this article for free. So if you look up the this line here is the DOI, which is just a document something identifier, digital object identifier. That's the one. So the DOI is just this string of numbers and letters. If you copy that and go to sci-hub.run. Okay. Go to this website. If you go here and copy paste that DOI into the field that'll appear there, I certainly think you should be able to access that for free, because I don't think anybody cares about my stream enough to be bothered by this. So yeah, if you just go to Sci-Hub, and sometimes it's a little bit silly, copy paste the DOI into that. No, you don't have it yet? Okay. How can we do this? Okay. All right. So I'm gonna look up some correspondence, make sure that it actually was published open access, because it's pretty crappy of them if they took that away for any reason. Otherwise, I am more than happy to just provide these, because it is like it is still authors are free to distribute their own work. So I'm more than happy to supply it, because I've just got it myself. Yeah. Aw, thanks. I appreciate that very much. But yeah, I'm gonna have to do some looking up. But if it is indeed not open access, then I will. I'll figure out a place, some kind of repository, maybe a Google Drive, something, where like I'll have like at least my published works for free. I'll put it into my Twitch profile and all that. So now I'm going to deal with some of the questions that I've seen from you but haven't addressed. The Nosferatu. So officially, no. Um, but unofficially, absolutely, Nosferatu is a reference to Nosferatu. Chemists do this all the time, just like twisting these acronyms and these abbreviations into references to whatever they feel like. So it is at least my headcanon that yes, this is 100% a reference to Nosferatu. Um, do publishing companies not notify clients about changes? No, they often don't really care very much about us. I don't think they really have to. Um, but yeah, it is definitely a bit of an L move on their part. Absolutely, not Nosferatu is just an absolute icon. Um, yeah. Hmm. Oh man. And I'm just realizing in my abstract, I didn't define what Nosferatu was refers to. Um, but in the paper, I do describe it. There's like a bit of an essay on what that is. But yeah, it's a really cool technique because this work was just like a really deep dive on the crystal structures of a bunch of these bunch of these compounds, these compounds with these polycyclic compounds, which just means that they've got multiple cyclic units, like this ring here, and there's a ring here, and then there's a little bitty ring here. So it's polycyclic. And so we just did a bunch of these compounds of several different types, and then just got really good, accurate crystal structures on them, and just did a really thorough treatment of this, and kind of we didn't introduce Nosferatu to the world, but there's a very limited number of publications that use this technique in crystallography, and it really genuinely should be the gold standard moving forward. Because the accuracy of these structures and the shapes of these they're called ellipsoids. So these represent a hydrogen atom, but whereas a hydrogen atom in reality is just kind of this little particle. It's just a little nucleus at the end of a bond. They're bonded to carbons. They're usually represented by little spheres, which is it's an approximation. It's a fudge factor, and because with using X-ray diffraction, it's very difficult, almost impossible to actually see hydrogen atoms, and this is because X-ray diffraction. It's basically what we use X-ray diffraction for is to do exactly like make pictures like this, like take a picture of a molecule, and use that to first of all to positively identify, like this is most certainly exactly what we have. And we know that there's bonds here, bond here, so on and so forth. So things like carbon, which is the dark gray stuff, and nitrogen, which is the blue atom here, those are relatively easy to see with X-ray diffraction. Because basically what it is we put the little crystals of these compounds. So it's not just one molecule, of course. It is a lattice of millions upon millions of these molecules together, and we shoot a beam of X-ray X-ray radiation at this crystal, and the X-ray beam gets deflected by specifically by the electrons in in these molecules. The electrons that are in their orbitals around the carbon, around the nitrogens, and the electron density that is between atoms and holding them together, which is just that's what bonds are. And so it's relatively easy to see carbons and nitrogens because those have quite a bit of electrons around them. There are quite a few electrons around them. What is it? 6 for carbon and 7 for nitrogen. So there's a fair amount of electron density there to reflect off of. This is added metal on the inside. It has a lot of similarity to that, actually. Yes, and so when we're firing X-rays at this crystal, at this lattice of these molecules, it deflects fairly easily off of the carbons and the nitrogens, but not the hydrogens, right? Because hydrogens only have one electron, and that is completely that electron is part of the bond to the atom that it's on, which is generally carbon, and so the electron that hydrogen has is not centered on the hydrogen. In fact, it's a little bit skewed towards the carbon because carbon is slightly more electronegative. And so this one and only electron that hydrogen has is not in proximity to the hydrogen atom itself, to the nucleus. It's kind of pulled away from it a bit. And so the hydrogen atoms, which is just a proton now, is really difficult to see, or is often kind of pretty much invisible to X-ray. But by doing, it's not quite like it being out of focus. It's more that it's just it forms kind of like a hole in the picture. It's something that just you don't get any deflection of these X-rays off of the hydrogen atom because there's no electrons, and so it's just kind of a blank spot in the picture, if that makes more sense. And so using this Nosferatu method, we couple the data that we get from the X-ray diffraction with this computational program. So it's just a very sophisticated computational software that says, okay, let's if there's a hydrogen here, here's how the electron density should be distributed around it, and so here is where you'd expect to find the proton. So here's what the actual bond length should be, and here's kind of what the motion of this hydrogen atom should be, which means that first of all, that these bond lengths between the carbons and the hydrogens are very accurate, and we compare this to a different type of diffractometry. That doesn't use X-rays but neutrons, and those do deflect off of the nuclei instead of the electrons. So neutron diffraction, hydrogens light up like a Christmas tree, and so we use that to get to kind of calibrate, here's what an accurate carbon-hydrogen bond length actually is. But the problem with neutron diffraction is that you can only do it when you've got basically a nuclear reactor or a particle accelerator on hand, and most places don't have access to that. So it's a very expensive process because you have to basically send your samples away to a neutron source, usually just siphoned off of a nuclear reactor, and get your crystals tested there. So it's very expensive. It's not a very accessible thing to do. Whereas X-ray diffractometry is very common, but has this problem of hydrogens being invisible. So it's extremely tedious, absolutely. But basically, so what we've shown in this paper is that you can use this computational method coupled with with a high quality X-ray structure to get these representations of the hydrogens and of the bond lengths, and we show that our results using that are extremely accurate, like very close to the accuracy of neutron diffraction. And so, like, it's just basically it's saying a lot of people have access to X-ray diffractometers, and they should be using this method because it is better, and we can prove that. And not only are the bond lengths accurate, so like the placement of the hydrogen atom is accurate, but also we can simulate the motion of these, because even in solids, atoms are not stationary. Even when they're in these tight crystal lattices where they don't have much room to wiggle around, they still wiggle around as much as they can. And so that's what these kind of oblong, like non-spherical representations of these atoms are saying, is that this is how much, like, if there's like this fixed point of like here's the carbon down here, and let's say the end of my finger is the hydrogen, it's still going to go like that, and it's going to do that very fast all the time. And so it's and that would be like kind of like motion blur. So like these atoms being kind of these ellipsoids instead of spherical is basically just like motion blur of these atoms, which becomes really important to the properties of these molecules and these atoms in the solid state, because that affects the kind of like how each of these molecules that are stacked up on each other, how they interact and how they kind of hold each other in place by all of these kind of additive forces between them. So yeah, so that's just like a bit of an overview of what this paper is talking about. But yeah, I'm going to look into why this isn't open access, and if it turns out that that's just how it is, and like I'll figure something out. I'll probably end up just making a Google Drive account, and I'll just link that in my bio here, just so that, because everything that I've published, I am determined needs to be free to the public. I don't like knowledge that I've contributed to be kept behind a paywall. So I like really appreciate you telling me about that, because I intend to rectify that situation. And thank you so much. There was a lot of very boring work that goes into this pretty boring paper, but like boring though it is very good science, and something that I'm quite proud of. Yeah. So, I wanted to ask you as well, like, Scott, how are you feeling about just like the concept of orbitals, and like if there's anything about the orbitals that you'd like me to go over again in a bit more detail, in a different way, just let me know. I'm very happy to go over it again. There's one thing I've found in teaching and tutoring is that like everybody is capable of learning this stuff. Like this is like part of my teaching philosophy. Like the foundation of it is that like I really believe that this stuff can be understood by anybody, and if it hasn't clicked for you, that's because I have not explained it in a way that works for you, and so like it's my responsibility as the teacher to facilitate the learning of this by finding a way to explain it that works for you. And I'm always willing to try and come at it from a different angle. Okay, so I'm feeling so about it. I think if someone were to ask me, I could recite about S, P, and D having different shapes, about electrons not spinning the same way in the same shell. Yeah. I think there are parts you don't remember because you're silly. Fair enough. Um, I mean, I will say to that, first of all, that it is not just okay. It is broadly preferable to be a silly little guy. I am very happy to be a silly little guy, but I will say I don't think you don't remember it because you're silly. I think you don't remember it because this is a crap load of information to take in, and it generally it takes repetition of like just being exposed to these concepts repeatedly to really like start to remember and start to process through these things. So. Let me just think about this for a minute. So, but like, I mean, the stuff that you put down about like knowing that the SP and D orbitals are they're different shapes and they occur in these layers around the nucleus, and those layers are like these energy shells, because like as you get further away from the nucleus, the attraction of the electrons to the nucleus, stuff that holds them together, gets weaker, right? Because just like magnets, the further away they get, the weaker their interaction is. Even when it's a purely attractive force, it gets weaker as they get further away. So that's one part of it, and the other part is that the electrons that are furthest away, that are in the outermost layers of the atom, they are like the attraction that they feel for the nucleus also decreases because of the other electrons between the nucleus and the outermost electrons, because it's this interference, and it's the other electrons interfere with that attraction, and it's called shielding. And so there's those two effects kind of decrease the attraction of the outermost electrons to the nucleus. So would their potential energy get greater as they move apart? So no. Well, to an extent, because there is a balance between this. So let me. I need to think for a moment of how to explain that. So actually, gravity is a really good analog to use here. So when we're just like kind of standing on the ground or on whatever, we are at this kind of like balance point, where like the force of gravity pulling us down is counteracted by the push of the ground on us, and so there's that balance, and you don't have to like. So like there's a certain amount of potential energy associated with that, because you can always fall on your ass, right? And when you do that, your potential energy converts to kinetic energy, and you hit the ground. And when that's the case, you have less potential energy, and you have to input work to stand up again. So you have to increase the potential energy by standing up. And of course, this is very, very much the case for leaving the surface of the Earth as well. You have to put work into that because gravity is pulling on you all the time. And so we have big old rockets that we use. to get us away from the surface of the Earth. And when you're doing that, your potential energy is hugely increased, right? Because you've got a lot more distance that you can fall, a lot more energy that can be converted into kinetic energy to make you a puddle when you hit the ground. Um, but at a certain point, uh, you kind of like you escape the gravity of Earth, and then uh, and then you don't really have the same kind of pull towards the Earth. Like if you're if you're like outside the solar system, you're not going to really feel any kind of appreciable pull towards the Earth. The sun maybe, but not really the Earth. Um, and so it's kind of like that. So like there's this increase in potential energy as they move apart. Because they're a nice stable state, their balanced equilibrium state is closer. So as they start to pull apart, there's a really strong attractive force that tries to pull them back together. And so that's kind of the analog here. But once you get further and further and further away, there's not really much attraction between them anymore. And so they like if they got close again, then they'd start to associate and attract each other. But yeah, like it kind of there's a significant drop off of that force with distance, right? Because the because a gravity. Oh, that's pretty. I'm so good at writing. Is what is it? It's mass 1, mass 2 over r squared. There's a constant in there somewhere. Some term. I'm just going to call it k because I don't know what it is. But yeah, so like the gravitational force between two objects depends upon their respective masses, but it decreases with the square of distance. So if you double the distance between them, the force between them reduces to 1/4 of what it was. So yeah, if you like if r was whoops. Yeah, so like if we just set r to 1, then it's just m1 times m2 over 1. But if we set r to 2, so we doubled the distance between the things, now it's m1 times m2 over 4, because 1 squared is 1, 2 squared is 4. And so the force between these objects, and there's an almost completely identical equation governs electrostatic forces. Like it's just a charge of one times the charge of another, divided by the square of the distance between them. So gravitational and electromagnetic forces are reduced by the exponentially with the square of distance. So like does that sort of make sense? What I'm saying? Are you smelling what I'm stepping in here? Nice. Yeah, we'll absolutely take that. I just want to make sure I didn't. Yeah, okay, I didn't miss any. Good. Yeah. All right. What am I gonna do? Ooh. All right. So we've got it. We've got a decision to make here. Because I'm completely torn. I have no capacity to make decisions right now. Would you like to talk a bit more about orbitals? I was thinking of maybe like explaining like let's like drawing out the d orbitals for you. Maybe talking a bit more about that stuff. Or should I just like go over this reaction and work on that for a bit? Because I don't think I'm going to do both. Because I've still got some work tonight to do for my prof. But I'll do one of these. And as the only person here in chatting, yeah, the decision's yours. Very good. Okay. All right. Well, let's talk about some orbitals again. Alrighty. Yeah. So we're talking about p orbitals and just the order in which we fill orbitals up. So, like for example, let's say we got something with I don't know, like 14 electrons, and really like that's all that I need to know in order to draw the electron configuration. So we've got 1s, 2s, 2p, and then we've got 3s. Whoops, that's not where that's supposed to go. So we've got 3s and 3p, and that will be enough. So 14 electrons. Basically, all we do is we write out the order of the orbitals, and then we just count out 14. So we start with a 1s, so 2 in there. The 2s, we do 2 in there. Now the p orbitals. Remember that when we're filling up orbitals, when you got orbitals that have the same energy, so like the p orbitals, you're going to fill them up. Put 1 electron in each of them first, because that is how we most effectively spread out the electron, the electron density. And then once all of them have 1 electron, then we start to pair the electrons up. So 2, 3, 4, and so that is 2, 4, 6, 8, 10 electrons. And so we're going to move on to the 3s orbital, which is 12, and then there's 2 left over for the 3p orbitals. Now, if we want to go from this to figure out like what atom are we looking at, if we assume that the element is neutral, which if you're not told otherwise, you should just assume that it's a neutral atom. So we've got two electrons in the 3p orbitals. So we're looking at the third energy level here. So it's going to be in this row. So right, because like the 3s orbital is filled by the sodium and magnesium. So if we put 2 electrons in the 3p orbitals, we got 1 for aluminum and 1 for silicon. Whoops, and that is not well circled. So the orbitals that we filled up correspond to a neutral atom of silicon. I never know whether to say silicon or silicon. I don't think it particularly matters. So, as I said, if it's a neutral atom, then it's like with 14 electrons. then that must mean that it has 14 protons as well, which is the kind of sounds like Tillicum. I don't know what to make of that. I am not familiar with this. Yeah, so we had 14 electrons, and if we're assuming that the element is neutral, which we should, then that corresponds to silicon, which has 14 protons as well. um, Now, if we had, well, let's say instead, use an orca. Oh, gotcha. Very good. But the important question is, did he sink any billionaires' yachts? And if no, no big deal. You don't get a lot of chances for that. But if yes, that's a good boy, and that deserves a treat. I'm so stupid. Okay, so another thing I'd like to do. So let's talk about if an element is not neutral, and what like how we treat the electron configurations of those. So if we've got, for example. So let's just talk about neutral fluorine. It did cause SeaWorld's stock to plummet into oblivion, which is really good, but the rest of the story is depressing. Oh dear. I mean, yeah, no, like I'm 100% with you. Anything that devastates SeaWorld's stock is probably a good thing in my book. Yeah, I can kind of speculate as to the rest of the story because like very, very large sea creatures kept in captivity usually do not have a particularly happy story associated with them. Is very sad. All right, on that note. Fluorine. So fluorine has 9 protons, which means that it also has 9 electrons when it is neutral. So if we set this up again, we'll take our 1s, our 2s, and our 2p. Very nice electrons, Ethan. Good. Okay, so we fill up our lowest energy orbitals, the 1s and then the 2s. And that accounts for 4 of our electrons. Again, we're with fluorine, which has 9 protons, and it is neutral at the moment. So we have 9 electrons, so we have 5 left to go. So 1, 2, 3, 4, and 5. All right, so this is the electron configuration for an atom of fluorine. But now, what if we have fluorine, a fluorine atom that has a negative charge on it? Which we see these things all the time. Like your toothpaste has sodium fluoride in it, which is just sodium plus and F minus. And it's a salt. It's a salt that contains the fluoride anion. And I should explain my terminology here. So in a compound like this, sodium and fluorine, the electronegativity difference. So basically, like how hard they pull on their outermost electrons is just one measure of one way to measure electronegativity. The difference is huge. Fluorine is has extremely high electronegativity. So a very, very strong attraction of a fluorine nucleus for another electron. It's very predisposed to having a negative charge on it because of very high electronegativity. Sodium has very, very low electronegativity. And when you have a compound that is made up of these two atoms with very different electronegativities, very high with a very low, you have what's called an ionic compound, where instead of being like a neutral atom of sodium bonded to a neutral atom of fluorine, because this would indicate like a covalent bond, which happens between atoms of similar electronegativity. This is no longer the most stable state of this molecule when the electronegativity difference is high enough. In these cases where we have this huge electronegativity difference, they're more stable as an ionic compound, where they do not share these electrons. Rather, these electrons are completely removed from the sodium and localized on the fluorine, and so we don't have that covalent compound or anything like it. We have this situation where we have sodium plus and fluoride minus, or fluorine minus, or fluoride. And so that is kind of the usual situation, because fluorine is so much more electronegative than most things on the periodic table. Like there's with carbon, which is quite a bit more electronegative than sodium. They do form a covalent bond, but a very polar covalent bond. So you have a partial negative charge on the fluorine, partial positive on the carbon, and that's a very strong bond itself. But I don't know why I erased all of that. Didn't need to. Yeah, so for a case like this, we effectively have a fluorine minus, and when that's the case, when you have a negatively charged fluorine. Oh, I forgot to define my terms. So in an ionic compound like that, you have the two components. The component that is positively charged is called the cation, and the negatively charged one is called the anion. So you can just remember. I remember these by being like, hey, the T in cation kind of looks like a plus sign, and the N in anion stands for negative. So that's my mnemonic for those ones. Yeah, don't worry about it too much. Yeah, so for a fluorine anion, there's a negative charge because there is an extra electron. Like anti. Sure, yeah, absolutely. Yeah, so in this state, we have a negatively charged fluorine, so it has an extra electron. And this is a very stable state for fluorine to be in, because the F minus, or the fluorine anion, has a full octet, right? Because the two s and two p orbitals are filled, which is the state of having 8 electrons, or sorry, not just electrons, but 8 valence electrons. And again, valence electrons are just the electrons in the outermost energy shell. And so that's the state. And so when you have 8 valence electrons, you have what's called just a full octet. This is kind of the idealized situation. This is things like carbon tends to form 4 bonds around it, because each of those bonds has 2 electrons in it, and that corresponds to having 8 electrons around the carbon, which again is a full octet. And so there's a couple different ways that we can kind of put 8 electrons around these atoms, and that's always the goal for these second row elements. the larger elements get a little. There's some differences there, but this is the basic principle: is that these always tend towards having a stable octet because that's the lowest energy configuration for these. And these are also called like noble gas configurations, right? Because F minus has the same electron configuration as a neutral atom of neon, which is the noble gas of the second row. And A. Let's move down here a little bit. So likewise, well, let's leave it neutral for now. So sodium would have an electron configuration that looks like this: 1s, 2s, 2p, and then 3s. So neutral sodium has sodium always has 11 protons. Neutral sodium has 11 electrons to offset that charge. And so we just fill up the 2p entirely, so that's 10. And then it has 1 electron in its 3s orbital. And because this electron in the 3s orbital is like really far away from the nucleus compared to like the 2p, because remember these energy shells get bigger. It's layers of the atom. So when you get to a new layer, it's further away from the nucleus, and so it's more loosely held because it's further away. I think next time I want to write down for myself that on Friday, I think what I'd like to talk about is effective nuclear charge, because that is that's kind of like the driving force, one of the driving forces behind this that I'm not going to explain today, but it'll make more sense when we get there. Don't worry about it. Suffice it for now that the 3s electron is further away, and so it is more loosely held by the nucleus, and so it's pretty easy for something like a neutral fluorine to just pick that electron up and remove it from the sodium, right? Because if you have because this sodium fluoride with sodium plus and F minus is like it. You can make it. There's a bunch of ways you could make it, but one way to make it is if you have just neutral sodium, so sodium metal, and fluorine. Got it. Must. I'll get there in a minute. So yeah, one way to make this: sodium metal and fluorine gas, which is exceedingly dangerous, but hey, it works. You don't want to be anywhere near this reaction because it's violent. This would be an extremely violent reaction. But if you react sodium with fluorine, you get sodium fluoride, which is just that compound up there with we drew. So got to keep everything balanced. So we have two atoms of sodium react with fluorine, because fluorine in its elemental state is just fluorine gas. So it's F2, kind of like oxygen is O2. So that's what you'd be reacting together, forms 2 molecules of sodium fluoride. So if that happens, like it's basically this neutral fluorine atom stealing the electron of the sodium. And when that happens, so we form sodium plus, and it's sodium plus because it's got 11 protons, but only 10 electrons. So you have 11 positive charges, but only 10 negative ones. So overall, you have a +1 charge, and that's because this. Let's take this away. So that's because that electron gets removed from the 3s orbital, and makes the sodium positive overall. But it's pretty okay. Like, sodium is pretty okay with being sodium plus, because now the valence shell of sodium is a full octet and has that same noble gas configuration as neon. So the net protons plus electrons determines the sign? Yes, exactly that. Exactly that. It's like fluorine or F minus has a negative charge because it has 9 protons but 10 electrons. So 9 positive charges and 10 negative charges. So it has an overall negative charge. Sodium plus has 11 protons and 10 electrons, so overall a +1 charge. That's exactly it. So the charge on an atom, on a molecule, on whatever, because this can happen on like a molecule scale as well. It's just simpler to think about it in the atomic scale. It's the charge of it is always just going to be protons plus electrons, and so positive charges plus negative charges, and so if they're equal, then there's overall no charge, and that's just a neutral species. Okay, so so in terms of going past the 3p, well, I don't know why I'm putting it up there. So 1s, 2s, 2p, 3s, 3p, and after that we get to the 3d orbital. And so just like with S orbitals have just this one slot for electrons, so they can carry 2 electrons. P orbitals have 3 slots, so they can take up to 6 electrons, but D orbitals have 5 of these slots. I don't know why I'm calling them slots. It's like, I don't think anybody's ever described it that way. But it's like, so I should say like there's one s orbital for the 1s energy level. There's 3 p orbitals in the 2p energy level. So px, py, and pz. But in d orbitals, there's what are the right? So it's so the designations for the d orbitals are dxy, dxz, d that's not right, dyz. Also, apologies. I am Canadian, so I say Z. I have not been corrupted by American English to say Z, but that's okay. So D Z squared and D x squared minus y squared. Okay, so there will be a pop quiz on Friday, and I expect you to. No, I'm just kidding. I will never just expect you to remember these. Um, there's, of course, there's reasons that they are named this way. No, I appreciate that. That's very gracious. Thank you. um, so yeah, like it on the surface level, it doesn't necessarily make any sense why they're called this. Don't worry about it. I promise it won't make a lot more sense once I draw these out. Um, but it's just kind of their names. So don't stress too much about it. Okay, so um, now I need. No, I need how do I do this? I used to be really good at drawing. Well, really good's an exaggeration. Of drawing three-dimensional axes. Z, X, Y. Okay, so I'm just going to leave this set of axes up here, and I'm going to leave it blank. But I'm just going to... I'm going to draw the other orbitals based on, like, this... God, words are hard sometimes. Labeling system. Sure, that's close enough. I'm going to make a bunch of sets of axes, and they're all going to follow this convention. Try to make them go straight through as much as possible. Okay, close enough. Okay, so I will name these. Okay, so this will be the DXY orbital. And so I'm going to draw two sets of axes for this one, actually. Let's make you red. Okay, so let's just... Okay. So first, I'm just going to... I'm going to draw this in 2 dimensions, and then I'm going to try to draw it in 3 dimensions. Mostly to show you that it's kind of hard to draw these in a sensible way. When I'm marking exams or something where like they have to draw the d orbitals, I'm pretty forgiving about how these are drawn, as long as they're not like obviously wrong. Because it's just really hard to depict 3-dimensional shapes on a 2-dimensional medium. So I'll try to give a couple ways of showing this. So if we're looking just like top down at the XY plane, so it's basically just like taking these axes and rotating them so you're looking directly down the z-axis, and then there's y in the kind of vertical direction and x in the horizontal. Except I've kind of set these on more of an x than a cross. It's fine. Don't worry about it. So if we're drawing this in this top-down view, this is what the orbital looks like. So remember I said like d orbitals kind of look like p orbitals, just that there's 2 of them set at right angles to each other. And so shading is very important. Always shade your orbitals when you draw them out like this. I don't remember where that sentence was going, but yeah, it's important. Always shade things. Yeah. Okay. So this is how it would look just from a top-down view. It's a little trickier to draw in 3 dimensions, but this being the x and this being the y, it would look kind of like this. Shading. Very good. That's actually not a very good picture of it, is it? It's fine. I'll just leave it. Yeah, so this... Yeah, that's kind of what it looks like in 3 dimensions. So the important features to look at in these d orbitals. So for these dx xy orbitals and so like dxy, dxz, and dyz are very similar. They do not, like the lobes of the orbital do not touch the axes. They are in between the x and y axes, and they don't overlap with that. Shoot. Okay, so this is English is becoming difficult for me at this point. So this is, once again, this is my cue to myself that I do need to wrap this up fairly soon. Yeah, so dxy and dxz. So again, with this being the x and this being the z, it looks like this. So in 2 dimensions, it looks exactly like the dxy orbital, except like this is now the z orbital. So it's just the exact same kind of prototype of this orbital, just flipped in a different direction. Just like px and py orbitals are just set at right angles to each other. That's exactly the same thing that's happening here. It's just the like kind of exactly the same shape and size of the orbital, just set on different in a different direction, a different orientation of the same orbital. Excuse me. So d, y, z. So this being, again, this being z, and now this being y, will look like this. Just need to think for a moment. There we go. Okay, so that's what they look like. So all of these 3 are exactly the same orbital, just set in different orientations. And I should look at it. Where's my... That's a pretty good one, actually. Okay, so yeah, if you look here, we've got so this one is dyz, this one's dxy, and this one's dxz. And you can see, like, they're just exactly the same, same shape, same everything about them, except they're just set on different axes. So just different orientations of the same orbital. Now, these are called like one name for them is is off-axis orbitals. So that's dxy, dxz, dyz. So they're called the off-axis orbitals. I think fairly straightforwardly because their lobes of electron density do not cross orbitals. They have these nodes along the orbitals. And again, like nodes are just these spatial areas of no electron density. So yeah, so these are the off-axis orbitals. Now, the other two, we got dx squared minus y squared. The name's a bit of a mouthful, and again, like these are named because of like the mathematical equations that define them. So like, yeah, it seems like a bit of a weird name, but just kind of don't worry about it too much. It's just a name unless you really want to get into the math, which I don't. So if we'll make another little 2D set of orbitals. So dx squared minus y squared. So these ones, again, this is the x-axis and the y-axis. So the dx squared minus y squared orbitals have, again, the same shape as the the off-axis orbitals, but these ones are directly along the x and y axes, and so these are these ones called the axial orbitals. Dx squared minus y squared, comma. We'll do that for later. Yeah, so in this one, again, x, y. Huh, that was pretty good. I did that fast. Look at me go. All right, I think I'm flying too close to the sun here. Gotta chill a bit. Okay. So that's what the dx squared minus y squared orbital looks like in 2 dimensions and in 3. Now, our last one is the dz squared orbital. Now this one is weird. This is the redheaded stepchild of the d orbitals, because it is in a category. Well, it's still in the axial orbital category, but it's completely different from this, and you'd never guess what the shape will be unless you're told. So I'll just draw it here, and we'll do our best. So again, the dz squared is also an axial orbital, flat like the Earth. Oh yeah, that's exactly it. Yes, yeah, it has an edge, and you can fall off of a dz squared orbital, but the government doesn't want you to know that. So, can we just take just a brief moment to point out how stupid the flat Earth conspiracy is? Because it's like I understand, like, conceptually how people can think that the Earth is flat. Like that's not the mystifying part of this. Like it's obviously wrong, and like trivially trivially proven that the Earth is not flat. In fact, like the ancient Greeks, Eratosthenes, calculated the circumference of the Earth. They knew in like thousands of years BC that the Earth wasn't flat. Which is also why I take a little bit of umbrage that some people are like they'll talk about how stupid and backwards people were in like the Middle Ages. Oh, they thought the Earth was flat. No, they didn't. No, that was not the accepted view in medieval times, or in ancient times, like maybe in prehistoric times, but but we don't know because we don't have any history to refer to. But literally like thousands of years ago, in it was at least 600 BC, when Eratosthenes calculated the circumference of the Earth. And I bet you anything it was known well before that. Where was I getting with this? Right. So it was never the accepted view. But the stupid thing about this is that like the conspiracy that's built up around the government is pushing this narrative of a round Earth, and NASA is just lying to you. It's like, why? Explain it like I'm 5. What do they get from that? How do they benefit from keeping this truth from you? It's just like, it's a conspiracy with no point. At least most conspiracies, like they've got a purpose. Like they've got it. They want to keep you complacent. Like they're actually lizard people, but they want you to think they're human so they can rule you in secret. That actually, at least it makes sense. But like, oh yeah, all world governments would have to work together, which they don't work together on anything. Like have you noticed how like nobody seems to sure, there's cooperation between nations, but not between all of them. There's always some sticklers, and it's just completely insane. Because there's no possible benefit that I'm aware of from them hiding this from people. It makes no sense. Yeah, no, and talking about like, don't get how the discovery of round Earth was from Columbus. Yeah, because it super wasn't. Nor even Magellan. Like, and because yeah, I've super duper heard about I've super duper heard people say like, oh, Columbus discovered that the Earth was round, or Magellan proved that the Earth was round. No, they didn't. That's wrong. That's an anachronism. And both of them, Magellan and Columbus, were horrendously horrible people. Just disgusting colonizers, slavers, just terrible people. But yeah, they didn't discover crap. Also, because you know what they discovered? They discovered lands that indigenous people had been on for millennia. So it's like good job. Yeah, I get a little worked up about this stuff. Even domestic wise, we still have whistleblowers like Eric Snowden. Oh yeah, so many like, I understand like some like need for some national security, but like by and large, I am very supportive of whistleblowers, just like people like Snowden, who just like see things that governments are doing that are gross, and they're like, hey, like people should know about this. Yeah, and again, because like just people will like, on balance, people will make better decisions when they have more complete information. And that is I think that is an axiom that is just repeatedly and ad infinitum proven over and over again. Didn't he also only step foot in the Caribbean? Yeah, I believe so. I think he was. Yeah, I don't think he went to the mainland at any point. I could be wrong on that. I'm not certain, but certainly the first voyage at least was to the Caribbean. But yeah, like even before that, like the Vikings made landfall up in Newfoundland, and but again, like they also didn't discover crap, because indigenous people have been here for very long time before that. Yeah, yeah. I just, God, I get a little worked up about I'm totally okay people being skeptical of widely held beliefs, facts, call it what you will, because like I understand very personally the kind of mindset that leads to that brand of skepticism, which is it's not a rational one, because when you cross the line between skepticism and just denying evidence, you've gone too far. But like I at least I understand that perspective of it, because again, I'm not going to spend any time on this or anything, but I was raised very, very conservative, religious, like young Earth creationist and all that, and I understand that mindset of this extreme skepticism that like takes a giant headfirst leap into just denialism. I understand it. I definitely judge it a little, but like not harshly, because like I mean, but for the grace of there being no God, there go I. Sorry, sometimes I make myself laugh. Anyways, but yeah, it's these conspiracy theories that just are just laughable. That I'm just like, you need to give your head a shake. Like if you can't even come up with a reason why every government in the world supports this lie of the round Earth and are keeping it from you, it's like, but for why? Like if you can't, if you don't have that, you don't have much of anything. But anyways, I have digressed very much. I would say appreciate that they're at least willing to be divergent from the norm, but I agree it can be a little silly. Yes, absolutely. Yeah, because following the crowd, or just like blind acceptance of kind of like what is the accepted view is that's not good skepticism either. It definitely, yeah, it absolutely gets really hard to talk with them about it, and because like you cannot reason somebody out of a position that they did not arrive at by reason, and so yeah, it's really tough to dissuade anybody about this. So like pretty much always I find when I'm talking to people who believe silly things is like, don't bother just like explaining stuff at them. Like that doesn't do any good. And then you just to them you just become like part of that oppressive majority that doesn't agree with them. So it doesn't do any good. What I've found to usually be like the best way to at least have a civil conversation is ask them questions about what they believe. Like, why do you think this is the case? What can you do to show me that you're right? You were raised in a similar place as a previously Muslim girl, right? So like both divergent ideas and common ones are impossible to refute if they're baseless. Yeah, no, absolutely. Yeah, I'm totally with you there, because like as like you can explain like for example, you explain evolution to a young Earth creationist until you're blue in the face, until you pass out and die. But like it won't move them an inch, because they just you can't. It's you can't do the same thing to them that they're trying to do to you, which is basically just proselytize your view of the world. It just doesn't help. And like I had even like to the point where when I started university, I was still like a pretty hardcore Christian, and a young Earth creationist. I didn't believe in an old Earth. I didn't believe in science, frankly. Even though, like this lasted until like probably a good like 2-3 years into my undergrad. And I'd had these things explained to me repeatedly, and it didn't work. It didn't do things. Um, but like it's when my beliefs got challenged, and when like I had to defend what I believed and found that I couldn't, or just like I found that like, other people had like that they defended their positions better than I did, um, and yeah, so like it's just yeah, it's just it's not a useful thing, uh, most of the time, because everybody's individuals, and but like most of the time it's not going to make any progress to just like explain things and be like, ha, that's a silly thing you believe, ha. Yeah, that just like people's defense mechanisms start to come into play, because like when and oh, there's a really cool study done by a neuroscientist. I cannot remember who it was at the moment, but like, so they did MRIs of people who were like had like deeply set beliefs of various sorts. Confirmation bias goes hard. Oh yeah, absolutely it does. So like this psychological study, like they did MRIs of people's brains while they were like while they were hearing like just like things that were contrary to their worldviews. So like, for example, I don't know what these people believed or what they were being told, but like for example, it'd be like just because it's topical right now. It's like young Earth creationist, explaining evolution to a young Earth creationist, and while they were hearing these arguments, the 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 part of their brain that activates under physical threat just lit up when they were just hearing these these things explained that went against their worldview, and like it's the same mechanism in their brains as when they're like being physically threatened, uh, and that is when like higher functioning thought shuts down in those cases. And so like just if you just like attack somebody's beliefs, even if you're right, even if all you're doing is just presenting them with like evidence, like here's what I believe and why, they can perceive that as a threat, or their brains do. Even like they may be cognizant that they're not under threat, but their brains don't know that, and so their brains will metaphorically circle the wagons around their worldview, and they'll just it serves to just get people to dig in on their belief and become less receptive to being convinced. So when these conversations are happening, it's important to do your best to not, like, depending on what your goals of the conversation are, and who your audience is. But like if you're trying to have a dialogue with somebody about their beliefs, and like even if you're trying to convince them otherwise, it's important to try to not trigger that response. Which is why like it's often best to just like ask them about their beliefs, and just like kind of probe it, and be like, okay, so like what would you expect to see if your view of this is true? Wonder if it occurs at the same magnitude on neurotypical divergence in different age groups. That's a very good question. Yeah, I would love to know if that's been studied as well, because that's a fantastic question. Yeah, absolutely, absolutely. Yeah, like those formative years where they're essentially like being taught a worldview by like the culture and the adults around them. They're stubborn as hell. Yeah, that's true. But like kids are learning machines, um, and And so yeah, I would be very very interested to know if that's been studied as well. I do not have a link to that paper right now. It's just one that I like kind of like had in the old archive of like, oh, I read about this once. But yeah, now I kind of want to look it up again because it's a super interesting question. Yeah, 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 yeah. Oh, and I just and I what do you say? I really appreciate your questions about this kind of stuff, like asking about even just right here, like wondering if it occurs the same magnitude on neurotypical versus neurodivergent people. That's a that's a great question. That's a question that hadn't occurred to me. So yeah, keep it up. Very good. Um, yeah, yeah, yeah. Yeah. Super interesting. I would, yeah. Let me know if you find. We'll meet back on Friday. Let me know if you find anything. If I remember to, I'll try to look that up as well. Because yeah, that'd be really cool to talk about. Alrighty. But yeah, you bet. I like and here too. Like, oh, I really that's the first time. I just well, I'm glad I can be that for you because Jay, like questions are wonderful things. Um, and like and when we're talking about chemistry too, like legit, you ask amazing questions. And like really really good, like better questions than I ever asked because I've always been extremely bad at asking questions, and in no small part because I was taught not to ask questions when I was a kid, and I was it's only in like my adult life that I've started to kind of like be taught how to question things, but that's neither here nor there. But you do such a great job of it to the point where like I have been teaching undergrads for 8 years. I've taught hundreds of students, and if if like if 10% of my students would ask questions like that were half as good as yours, and with that frequency, like I'd be thrilled. Um, and because like it's just it's just I want you to know it's genuinely not common to get the quantity and quality of questions as you give me, and like it's a great thing for somebody like me who like just really loves teaching. I love getting questions like this, which is why like I never want you to apologize for asking questions because they're great and I enjoy them. All right. I do my best. But I like this is how the world gets better. Is people asking questions and people trying earnestly to answer them. So hey, let's keep it up. You and me are doing great. um, all right. So I'm going to finish up just drawing out the d orbitals, and then I think I got to call it for tonight because I got a bit more work to do, and I'm getting a little fried. Oh, I forgot to eat supper. Huh. Okay. So sometimes I get a little distracted, and I forget to take care of my meat suit. Um, and I'm realizing that my flesh bag is hungry. So I should sign off pretty soon and get something to eat. All right. So the dz squared orbital. So let's do another 2D representation of this. Let's do it bigger so you can actually see it. How are we going to do this, actually? Well, no, we're not going to do that. Better get you. Surviving your third can of Diet Coke. Too lazy to cook, too busy to stop learning. I love that. Cooking can be outsourced. Learning can't. So, yeah. Alrighty. Actually, I kind of don't think a 2D representation of this is going to be that useful. Okay, so a dz squared orbital it's real weird. So you've got your usual kind of. I want to draw that better. Okay, so we've got the usual like p orbital type lobes of electron density, and that is directly on the z-axis, right? Because this is an axial orbital, which means that the electron density intersects with the axes. So this is on the z-axis, just like these ones are along these axes. This one's on the z-axis. And here's where things get strange. So the other part of the dz squared orbital is like this. So I'm going to shade this one, and I'm going to leave this unshaded. So this here is like this little donut of electron density that is in the it's in the xy plane and goes fully around the z-axis. Yeah, right. Like it's just you'd never see it coming, and yet that is its shape. So like actually, if we do a 2D representation, so I'm going to put the z-axis up here and the x here. So just flipping the axes a bit. So yeah, we've got this one along the z-axis, and then we've got this little guy. The little donut of it is like just a ring around that is in the XY plane. Yeah, so I'll go back over here and we'll look at this guy here is the dz squared, and it is a strange little duck. But it's what can I say? That's what it is. It's like all of these shapes are mathematically derived, which I think is a really good reason for. It has been a really good reason for me to not go too deep into the math, because math is weird. It makes things that look really, really strange, but it works. Like that is the mathematical solution to where you'd find the electrons in that type of an orbital. So yeah. Yeah, math is a strange thing. Yeah, so I think that's as far as I'm going to go with this right now. But yeah, so these are the 5 different orbitals that you find in a D shell. Yeah, so the XY, the XZ, and the YZ are the off-axis orbitals, because they don't cross any of the X, Y, or Z axes. And the dx squared minus y squared and dz squared orbitals are axial orbitals. That their electron density is centered around the axes. Yeah. So these are weird. And again, in just like the p orbitals, all that these represent is different orientations of electron density around the nucleus. And in the absence of any outside forces, which is to say, like, if this is just like orbitals around an atom that is just completely by itself, nothing else around it, all of these orbitals are degenerate. They have exactly the same energy, and so with no other outside influences, you could fill up any of these orbitals first. Like if you're populating them with electrons, it doesn't matter which one you start with because they have the same energy. Now this is not true when we have like when these are parts of molecules, uh, because once you have molecules, now you've got you've got your atom that we've been looking at that has these electron densities and all these different p and s and d orbitals. Um, but once you have other atoms in proximity, those atoms also have electron density, and so they'll squish up against each other, and because again, it's all about minimizing electron repulsion. So they will twist and contort in different ways in order to spread out the electron density of the entire system, and 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 the orientation of these orbitals will start to matter, and they will now not be the same energy. And just a really, really quick example of that is if we have, whoops, that's just a mark. Clowns and cars. Yeah, exactly. Yeah, for sure. Yeah, like, and this is one thing. Like, a lot of students have trouble with remembering that atoms, molecules, orbitals are not these rigid things that you put them in a place and they stay there. These things are always in motion. These things, like the atoms and the molecules, are always in motion, and usually several different types of motion. And like these orbitals are squishy. When one orbital comes up against another orbital, they'll either, like, depending on the phases, if they're the same phase, they'll like smush and interact and become one larger space of electron density, but that changes its shape. And if they're of opposite phases, they'll squish and they'll squash and they'll twist and contort, and but those ones cannot overlap. Could they ever stop moving? No. Like the short answer is no, because in order for something to like completely stop moving, it would have to be at like it would have to be at absolute zero. That like minus or 0 degrees Kelvin, which is that absolute scale, where it has no heat, it has no energy, except for like the mass energy of the thing. Now, absolute zero is effectively a theoretical concept, because if something were ever to get to absolute zero, it would violate the Heisenberg uncertainty principle, right? Because it would have a strictly defined and static location, right? Because the Heisenberg uncertainty principle says that that the more precisely you know something's position, the more uncertain is its momentum, which is the direction and magnitude of its velocity. And conversely, the more precisely you know the momentum of a thing, the more uncertain its position. So if something was at absolute zero, you could theoretically, like, it would have a definite and static position. But then because quantum physics is really weird, that thing would now have an infinitely uncertain momentum. So it could be going in any and all directions at the same time, which is just like this logical absurdity. And so, like, basically, things can't get to absolute zero because they are in a system with energy. There's something else I was going to say about that, but it's gone right now. Maybe it'll come back. We'll see. Yeah. What was it? Oh, right. I was going to say, like, we can, or like physicists have gotten things to insanely low temperatures. Like if like the freezing point of water is 0 degrees Celsius, and like nice balmy weather is like maybe 25 Celsius. So it's like 25-degree difference between comfortable for us and really heckin' cold. Absolute 0 degrees Kelvin, is minus 273.15 degrees Celsius. It's really, really cold. And so, but like, physicists, chemists, scientists have, like we make things extremely cold kind of as a matter of routine. Like a lot of our instruments are nitrogen cooled, so like they're brought down to the temperature of liquid nitrogen, which is I think roughly, yeah, superconductors. Absolutely.
Mic on. Mic off.
Whoops. So okay, so superconductors are okay. Oh, where am I going to start? Sorry, I've got like 8 thoughts simultaneously, and it's just a traffic jam in my brain. So yeah, liquid nitrogen, very, very, very cold. Really fun to work with though, and very safe. It's fine. But like some of our instruments, we cool with liquid nitrogen, and that gets to about 100 degrees Kelvin. So that's about minus 173 Celsius. So like our X-ray crystallography, we do that at 100 Kelvin. Which is extremely cold. And what that does, you remember in those crystal structures, the atoms were not spherical. They were these ellipsoids because of that motion blur, because they're always vibrating back and forth. And that was at minus 173 Celsius. And we cool it there because as you cool it, they vibrate less. They go from like, yeah, going like that to like vibrating a little bit like this, and we still get these like big ellipsoids that are saying like this thing's vibrating quite a lot, and that's at like roughly liquid nitrogen temperatures. It's a little bit above, but not by much. So we cool things in crystallography. We cool it down to liquid nitrogen temperatures, so we can get a better picture of the molecule and make those ellipsoids smaller, so we know more precisely what the locations are. But we can go way colder than that. And as far as I know, we don't have any superconductors that operate as superconductors at liquid nitrogen temperatures. Is the amount it vibrates linear to the temperature, or is it different? That is a great question. I do not think it's linear. I think it would look more like an exponential curve, like probably a pretty shallow one. So you probably get something like that, kind of at. So this, if this is like the amplitude of the vibe. Oh no, that would be amplitude of vibration. What am I doing? What am I doing? I've drawn a weird graph. Don't worry about it. So like at like the amount that it vibrates goes down and down and down with lower temperature, and like at infinity, like infinitely small values of temperature, then it would almost not be vibrating. And like, oh, and we're going to get to like I'll tell you how close we get to absolute zero sometimes, because it's wild. It gets really crazy. And at those temperatures, you have extremely small vibrations of these things, and that's very important. And I'll tell you why in a minute. So, yeah. So superconductors are these materials that conduct electricity without resistance, and that only happens at really low temperatures. And and it is like one of the really really big things that people are pursuing in science is a superconductor that superconducts at liquid nitrogen temperatures, because liquid nitrogen is super plentiful. It's very very inexpensive because I mean our atmosphere is 70% nitrogen. All we have to do is cool it down until it becomes a liquid, and that's really easy to do. Uh, so, like, if we were to make a superconductor that operated at liquid nitrogen temperatures, they would become really, really viable all over the place, and so we would immediately have huge advances in what we can do, and like engineers would have a heyday with it. Excuse me, but. So we have to go colder than liquid nitrogen in order to have superconductors. And so I think I talked about this a little bit when I was talking about NMR, the nuclear magnetic resonance, because those are set in inside of these coils of copper wire. It's an electromagnet, but it's cooled with liquid helium. And at liquid helium temperatures, copper is a superconductor. And but like liquid helium, oh boy, it. Okay, so I'm gonna say, hold on. Okay, so room temp is about about 298 Kelvin. Freezing, like the freezing point of water, occurs at 273 Kelvin. L N2. That's just the notation for liquid nitrogen. That occurs at around I think it's like 80 or 90 Kelvin. I think it's around 90. What is it? It's Fahrenheit. Come on. Sorry. Minus 196. Come on, Kelvin. Okay, so 70. Okay, I was off by a bit. So liquid nitrogen is about 77 Kelvin. Liquid helium, specifically helium 4, is. I want to check on this because I was wrong about. I was wrong about nitrogen, so I want to double check about this. Okay, 4. Yeah. So liquid helium. Oh yeah, liquid helium exists, although it is much more rare, for a couple reasons that I will get into. So yeah, liquid helium is about 4 Kelvin. All elements could be a liquid. I don't think all of them could be, actually, because there are. Oh man. So here's another idea of things I could do at some point. Tutoring topics. Phase diagrams. Okay, so I was just writing something down for like something I want to go over at some point. So there's these phase diagrams that show you like at different temperatures and pressures what state certain compounds or elements will be in, and basically like at a certain combination of temperature and pressure, you could get pretty much anything to be a liquid. But like if you're only changing the if you're only changing the temperature, some things will never be a liquid. Like they'll go straight from solid to gas. Um, things actually like carbon dioxide. It's you can make carbon dioxide a liquid if it is at very high pressure, but if it is at kind of like normal atmospheric pressure, and you cool carbon dioxide, it will go straight from gas to solid. And if you warm it up again, it'll go from solid to gas. It's called sublimation. And so yeah, there are some things that will not like naturally occur as a liquid. But like lots of things can occur as like, well, pretty much anything given a certain temperature and pressure. I think almost anything could be a liquid. But yeah, so helium. Helium gets down to 4 Kelvin. And that is kind of the temperature regime at which copper will become a superconductor. And science looked at that and we said, that's not cold enough. And so we have things like liquid helium-3. So it's just an isotope of helium. It's got one fewer neutron in the nucleus, because helium-4, which is the most common isotope, has 2 protons and 2 neutrons. But helium-3 has 2 protons and 1 neutron. So it's lighter, and its temperature is roughly 3 Kelvin. And like, you may think that's a pretty small difference, and like, yeah, it's only a difference of 1 degree, but that can make that can have a really big impact. And the thing that we use it for the most, and I would argue its most important use, is in like space telescopes. And it's like detectors out in space, because if you're like with the kind of sensitivity that these instruments have, the temperature of the circuitry in these instruments is high enough to create like this noise in the readings, and so it like you know, kind of like the wiggles in the baseline of their spectra can be minimized by cooling the instrument to colder and colder temperatures, like as low as possible. And helium-3 is kind of like the best chemical way to cool things that we have. And so like by cooling these down as much as possible, even by 1 degree Kelvin between helium-4 and helium-3, that makes a big difference to the amount of noise that you get in these telescopes. And so minimizing that noise lets it be more, like, makes these instruments more precise. And like things like the James Webb Telescope, but like a lot of like infrared detectors in particular. Mostly like infrared detectors, which the James Webb Space Telescope has, because it sees fairly far into the infrared region. Because like infrared, of course, is like it can typically be viewed as like just heat, which is like you feel heat. It's a lot of it is infrared radiation. There's a lot of nuance to that, and just like saying that heat is infrared radiation is not correct. But they tend to operate on the same wavelength. This infrared radiation, and just like the temperature of the circuitry. So like this is kind of the temperature of our best instruments out in space that take the most precise measurements. But we can go lower. Just like because science says 3 degrees is too high, we can do better. So like there's like some really advanced like particle physicists can cool certain systems down to microkelvin. So it's like 0.00000 x, like Kelvin. So So like physics labs can use some really interesting tricks with like I don't know lasers and stuff. They can do some really cool things to get stuff down to like micro Kelvin, which is mind-boggling. Like it's so close to absolute zero. Um, but like and because it's so close to absolute zero, the position of the particles that they're looking at can be really precisely known and controlled. So like this is where they have to start compensate like where they are stymied by these quantum effects of like confining the position of these particles and like but like they're the momentum of these particles becoming less and less certain as they get to it's there's so much cool stuff that they can do at these temperatures. It's very very neat. uh, okay, so it is I I said so long ago that I was going to sign off and be done with it, but to hell with it. I am on an ADHD rabbit trail and I cannot be stopped. So, but the actual last thing that I'm going to go over is helium, because helium is so incredibly important to science because it makes things superconducting like NMR. It's so important in the medical field because they also have to use liquid helium for things like MRIs. And like because these things do not work unless they have these superconductors that we can only get at these liquid helium temperatures. And the problem with this is that helium is a non-renewable resource. Because helium is a gas. There's traces of it in the atmosphere. Oh yeah, we're gonna talk about the balloons, which is like the chemist's greatest pet peeve is people using like wasting helium in balloons. It's offensive to me. But yeah, and it's offensive because we have these helium shortages because we do not get helium from the atmosphere because there's too little of it, and because we lose helium to space all the time. It just floats away because it's so light, right? Because helium has a really low density, which is why when you breathe in helium and talk, your voice comes out at a higher frequency because the helium gas is less dense than our usual atmosphere. So you have vibrations in a medium that has lower density, and you have a higher frequency. So helium out in the atmosphere, we can't capture it efficiently. Effectively, we can't do it right now. And so it gets lost to space. It floats away and it's gone. And so the only source of helium that we have is from rocks in the earth, largely like uranium. And like other things that undergo alpha radiation, because alpha radiation is just the emission of a helium nucleus, two protons and two neutrons just stuck together, and they just zap out of a thing. That's just radioactive decay. So we get our helium mostly from underground. We get it from mining operations, usually for like natural gas. You get a lot of helium mixed in with the methane. Because of these radioactive processes that happen in the Earth's crust, where like you just like get helium trapped in these pockets. But it's because of radioactive decay. It's because of rocks doing radioactive stuff in the ground. That's where we get helium from, and we don't have a whole lot of it, and it's so critical to so many scientific and medical instruments, that it's completely crazy to me that people put this stuff into balloons, because it's a precious resource, and it's just it's crazy to me. It is is a deep set pet peeve of a lot of chemists and physicists that we would waste it with, because it's not renewable. It's genuinely pretty scarce. Um, so yeah, just boycott helium balloons forever. At least until we find like liquid nitrogen temperature superconductors, and we can just use nitrogen instead of helium. So, anyways, that's this has been my TED talk on why I hate balloons. Carbon dioxide balloons, sure, why not? Absolutely. Oh man, okay, all right. I said that was the last thing, but this is going to be the last thing. Um, Sodium. Oh God. Okay, so that's. I mean, we could do that if you want it, if you like exploding balloons, that's a good that's a good way to do it. I love it. Oh man. Um, right? Yeah, you want people to be talking about your party for years afterwards. That's how you do it. Absolutely. It's like if your party has a body count. Yeah, it's it's been a good time. Oh God. Oh, somebody stop me. Um, yeah, yeah. I enjoy playing with cryogens like carbon dioxide, or like with just dry ice, and liquid nitrogen and stuff like that. There's lots of fun things you can do. And liquid nitrogen, one thing I really like is you can make ice cream with liquid nitrogen. And it just takes a few minutes. You get all your ingredients for the ice cream in a bowl, and you wear some really thick gloves like oven mitts, and you usually need two people for this. One person pouring the liquid nitrogen and the other stirring the stuff. And within maybe 5 minutes or so, you can make a batch of ice cream just using liquid nitrogen, and it is delicious. It's such good ice cream. It's so fresh. Oh, I love it. It's so good. I've done it a bunch of times for different groups. It's lots of fun. Anyways, my good friend, it is like 9:15 where I'm at, and I am tired. I am a hungry boy, and so I am going to sign off. But it has been just absolutely lovely hanging out with you as always. I will be back on Friday, and I hope I'll see you there. I hope you have a great week. You take care of yourself, be safe, and yeah, I will see you next time. Okay, bye.